let's continue what we did last time. Last time we talked about the elimination method to solve linear equations. The key idea is once we have multivariable linear equations, then what we do is we're trying to
1600s, and the mosquitoes originated from South Africa.
What we're trying to do is we try to eliminate certain variables so that we get lower small number of variables. Then we solve our equation. Okay, the three operations are valid. Rule operations. Okay, rule operations. We can swap the two equation position of two rules. We can multiply a rule by non-zero numbers, non-zero scalar, or we add a rule, a scalar multiple of another rule. Okay, so this is the, the three operations, rule operations, they are invertible. We can do backwards thing. So we do not add anything new. We do not lost any information. Okay, so this is equivalent. Let's do some examples. Okay, let's see this example. Okay, let's see this example. X plus Y plus Z is 7. Make it bigger. Okay. X plus Y plus Z is 7. And then X plus Y minus Z is 5. X minus Y plus Z is 3. Okay, now when we solve linear systems, we can forget the variable, the name of the variable. So we can just manipulate the coefficients. Okay, so we write down the augmented matrix. Okay, so X, Y, Z coefficients Y, 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 and then the other thing is 7. And then we write X, Y negative Z, so it's Y, Y negative Y. Then it's 5. Now we do rule operations. The last equation, so it's Y negative Y and Y, and the coefficients, and the last entry is 3. Okay, then we do rule operations so that we get upper triangular matrix. Okay. Okay, you see, we do so this is R1, R2, R3. So to cancel the first entry of column 2, root 2, the first entry is 1. So we use negative root 1 add root 2, substitute root 2. Okay, then root 2. So root 1 is fixed. Y, and 7 here. And root 2, we add negative root 1. Okay, so we get a y add negative 1, so we get a 0. Y add negative 1, so we get a 0. Negative 1 add negative 1, so we get negative 2. 5 add negative 7, so it's negative 2. And then we do negative root 1 added to root 3. And then substitute root 3. So then we get 1 plus negative 1 is 0. Negative 1 plus negative 1, negative 2. And then 1 plus negative 1 is 0. And then this we get a negative 4. 3 plus negative 7. Okay. And then so this is not upper triangular. So we can switch the rule with root 2 with root 3. Okay. So root 2 and the root 3, they switch with each other. Okay, so we get a 1, 7, and then we get a 0, negative 2, 0, then negative 4. This we get a 0, 0, negative 2, negative 2. Okay, And we can continue go on, simplify this. Okay, we can also, divide, multiply a root by non-zero number. Okay, for instance, we multiply root 2 by -1/2. So root 2 multiply -1/2 root 2, replace to root 2, and then multiply -1/2 to root 3, replace root 3. Okay, so this we get a 1, 1, 1. This we get a 0, 1, 1, 0, 0, 0, 1. On this side we get 7. We get a negative. So we get a -4 times -1/2. So we get a 2. In the last entry, so we get a 1 here. Okay, so we continue. So this is root 1, root 2, root 3. And then we can root 1. We cancel the last two entries of root 1. Okay, so we get R1 subtract R2 subtract R3. Then replace R1. Okay, so what we did is we add root 2, root 3 to root 1. Replace root 1. So this we get 1, 0, 0, 0, 1, 0, 0, 0, 1. This we get 7 minus 2 minus 1. So we get a 4, 2, 1. Okay. Now, if you write down the equation, what do we just get is, if you write down the corresponding equation, linear equation. So this, the first rule tells us coefficient x is 1, y is 0, z is 0. So this we get a x is a 4. And the second rule tells us no x. Okay, the first 0 corresponds to 0x. And the second rule, second entry 1. So the second, we are talking about the second column. Second rule. The second rule tells us that 0x, 1y, 0z, which is 2. The third column, third rule tells us 0x, 0y, 1z is 1. Okay, so we actually solved this linear equation. X, y, z. We find the value. Okay. Okay, another example. Maybe a little remark about this problem. Now, if you write anything as matrix multiplication, so if you write x as x, y, z, and then you write the coefficient matrix A as the coefficient matrix 1, 1, 1, 1, 1, -1, 1, -1, 1. Okay, so you can write this equation as AX, which is B. Here the vector B. The vector B is 7, 5, 3. Okay, so we get a solution. Here, this matrix is invertible. So what we actually essentially get is X is A inverse B. A simple question in linear algebra is, given a matrix, try to determine whether this matrix is invertible. If it is invertible, find the inverse of this matrix. Now, when we solve this equation, actually, we are actually, in some sense, using the inverse to this system. Okay, we are trying to invert the thing. Later, we will push this idea, trying to use elementary rule operations, try to find the inverse of a matrix if it is invertible. Okay, if it is invertible. Now, let's see one example that when a matrix is not invertible, and see what happens. Let's see this equation. Now let's see this equation. We just modify a little bit. X plus y plus z is 7. X plus y minus z is 5. Negative x, negative y plus z is 3. Now, actually, you see, this is a little modification of, so this equation is just a little modification of the last equation. So we just modified the equation 3. Okay, you just see we modified the last equation x minus y plus z. We modify it to be negative x, negative y plus z. Okay, we just, the other equation are the same. Okay. Now this just a change of this coefficients. It turns out actually the conclusion actually changed. Now if we write down the matrix, if we write down the augmented matrix, then what do we get? We just compare coefficients, y. Now this here we had 7. Now this is the y, negative y, 5, negative 1, negative 1, y, 3. This is the augmented matrix. Now if we do root operation, you see, now you see root 2 plus root 3 replace to root 3. We use root operations, and then the other rules we fix it. Now 1 plus negative 1 we get a 0, 1 plus negative 1 we get a 0, negative 1 plus 1 we get a 0, 5 plus 3 we get 8. Now this corresponds to the equation. If you write down the thing, correspondence. Now the first rule is just first equation. The second rule is just the second equation. But the third rule, you get a 0x plus 0y plus 0z is 8. So you see, you get a 0 equals 8. Now this is, of course, 0 equals 8. This is contradiction. Okay, this gives contradiction. So there's a contradiction. Contradiction. 0 equals 8. So that's no solution. So the linear system. The linear system has no solution. Okay, now the reason that the linear system has no solution, what is the geometrical meaning of this thing? Now, if you look at the equation 2 and 3, you see for equation 2 and 3, there are two lines, there are two planes. Okay, there are two planes. And if you look at the normal vector, 1, 1, negative 1, negative 1, negative 1, 1. So the normal vectors are parallel. Okay, normal vectors are parallel. This means the two planes are actually parallel. Okay, so the reason that two planes are parallel, then they have no intersection. So this shows why this linear system has no solution. Okay, so the reason is for this why there's no solution is the two planes. So the two planes defined by equation 2 and 3 are parallel because they have the parallel. Okay, because since the normal vectors are parallel. Okay, so this means two planes has no intersection. The two planes have no intersection. Which means there cannot be solution. The linear system, the given linear system has no solution. Okay. Now you see when we do linear elimination question.
Yeah, I just want to make sure that so the planes are parallel because like when you add like row 2 to row 3 or row 3 to row 2, like you get 0. That's what makes them parallel.
Parallel here, now as long as that is a special case, if you get a 0, then actually they are parallel. Now actually sometimes you may not get a 0 equal something. For instance, so here the equation, let's just look at the equation 2 and the equation 3. You see equation 2 and the equation 3. So equation 2 is x plus y minus z equals 5. So if you write down its normal vector, the normal vector ny is the coefficients of x, y, z. It's 1, 1, negative 1. Okay. Now the second equation is negative x, negative y plus z is 3. So if you write down the normal vector is negative 1, and 1. Okay, you see n1 is actually negative n2. They are opposite direction, but they are actually parallel. Okay, so if you see here this plane, suppose this is the plane defined by equation 2. Now it has normal vector, normal direction n1.
Okay, so they're parallel when they're like negative of each other.
Yes, yeah. Actually, a more general thing is as long as they are a multiple of another, they are a multiple of another thing, they are parallel.
Okay.
Yeah. So here you see n2, but n2 here is negative direction n2. Yeah. So you see this plane define the two planes. As long as their normal vectors are parallel, then the two planes they should parallel. Yeah. So they have no intersection. Yeah. So two vectors are parallel with each other if if they are a multiple of another. Okay, any other questions? Okay, now you see if two planes are parallel to each other, then if you use linear, if you use rule operations, actually you should get a rule of zeros, 0, 0, 0. Okay, now this is because these two planes are parallel, but the two planes does not coincide. If two planes coincide, then this equation will be identical. Then you will have two planes identical. So if you just subtract, then you get 0 equal to 0. 0 equal to 0 is not a contradiction. So this is true all the time. So this is redundant. Okay. So in this case, this is not a contradiction. So you can continue go on in this manner. So a necessary condition such that the equations, the linear system have solution is once you use rule operations, you cannot have a rule of 0, 0, 0, and the last entry is non-zero. Okay. In that case, you have a parallel thing. So that there's no solution, no intersection. But it's another story if two lines are identical, such that you get a bunch of 0, 0 equal to 0. Okay. So homework for this section is given certain linear system, you should know how to do elimination. Okay. The key idea is try to use multiples of certain rules added to another rule, such that you cancel this entries of a matrix, such that you get upper triangular matrix. Okay, you get upper triangular matrix. You see here what we did is, you see what we finally get is this, for instance, this matrix. You see we have a bunch of zeros in the left corner, left lower corner. You see this matrix. In the left corner, we have 0, 0, 0. The left corner is 0. The diagonal entry is below the diagonal entry. There is no non-zero numbers. Okay, so this is the upper triangle. This is called upper triangular. Okay, once we get upper triangular, and then we can substitute back. Use backward substitution. Okay, so this is the method of linear elimination by root operations. Okay, homework for this section is we have a so this 2.2, number 11, number 13, number 17, 27. Sorry. Okay, now we continue another technique. Now we have seen we can use linear elimination to solve linear systems. Okay, the key technique is try to construct the augmented matrix. Then we use root operations to obtain an upper triangular matrix, and then we use substitution. Now actually we can use, you see, matrix gives us an operations, so that we can achieve these operations, root operations, by matrix multiplications. So this is the idea. Okay, so we have seen that we can use root operations. So we have seen that when we use root operations, we can do root operations. For elimination, use elimination method to solve linear system. Now, these operations can be done by matrix multiplications via matrix multiplications by certain specific matrix, like some elementary matrices. Example. Now we want to swap two rules. Okay, example. Matrix that swaps two rules. Okay, this example. Let's say use this matrix P12. Is swap this matrix P12 swap the first rule with the second rule. Okay, now the first column tells us what we get, what output that we get if we input I. So the first column tells us it's a 0, 1. This means we output a 0, 1. If you plug in 1, 0, which is I, output is the first column 0, 1. Now the second column is J equal to J is 0, 1. Okay, J is 0, 1. J is 0, 1. And then the second column tells us the output of J, which corresponds to 0, 1. Okay, 0, 1. Okay, then if you multiply P12, okay, XY. Okay, this is, you got P1. If you write this thing as X0 plus Y0Y. Okay, 0, 0Y. What we get is, if you by the linear property, you get, okay, P12 0 X0 plus P12 0Y. Now this you get, plugging X0, you get a 0X. Plugging 0, y equal to y 0. You add them together, you get this actually yx. I.e., you plug in xy, the vector xy, the output under this rule operation swap to the rules. Here the rule xy. Okay, we have two rules. Each rule is actually dimension 1. It's just a vector, one dimensional. So it's the yx. Okay. Okay, so this is the swap two rules. Now, what happens if we want to swap root 2 with root 3 and keep the root 1 fixed? Okay. Now P23, which is actually this matrix, 0, 1, 1. Okay. So plug in I, output I, it tells you the first column. Now, if we plug in J, what do we get? We plug in J. The second column gives us the image of J. So we swap the second rule with the third rule. We plug in J, then we should get K. Okay, K. K is remember 0, 0, 1. This gets K. Okay, if we input K, then we should get J. Now J is 0, 1, 0. Okay, so you can check. P23 times xyz is the x gives you x the first column, y gives you the second column, 0, 0, 1. Z gives you the third column, 0, 1, 0. So this you get x 0, 0. This you get 0, 0, y. This you get 0, z, 0. So you get, you should actually add them together, x, z, y. So, okay, i.e. you plug in x, y, z, output under this operation 2, 3. Then you switch. The third rule is the second rule, x, z, y. Okay, i.e. P23 swaps the second rule with the third rule. Okay, very easy. Now, of course, if we swap once and then we swipe it again, we just back to original thing. Okay, i.e. for instance, P12, we do this operation P12, and then we do this this operation swap P root 1 with root 2. Do it again. So this actually you get nothing. You switch nothing. So this is identity matrix. Okay, nothing changes. Similarly, you got a P23 times P23. So you got a P23 squared is actually I. Okay. So I is identity. I means identity. Okay. Nothing changes. Okay. Here is a definition. If operation twice a square of this operation is identity. So definition. M is called M. It means matrix. M is called an evolution. If M squared equals I. Here I means identity. Okay. Now this kind of evolution plays an important role in classification of finite simple groups. This is another story. But you should know that evolution plays an important role in algebra. Here you see we have P12, P23. They are evolutions. Okay. Now similarly, you can write down P13. P13. Okay, P13. P13, of course, P13. How do we write down P13? Now here 2 is keep fixed. Now we switch 1 with 3. First rule is the third rule. If you plug in I, okay, now you should get switch to key, okay, key. So you plug in I. The first rule gives us the image of I, so we get a key. In this case, we get a 0, 0, 1. Okay, this is the key. Now the second rule is keep fixed. So this is the we should plug in G. We should get G. To get a 0, 1, 1. Now plug in key. So it's switch 1 with 3. So it's plug in key. We should get I. Okay, 1, 1, 2, 3. EJK. So plug in key get I. So it's I is 0, 1, 1. Sorry, 1, 0, 0. Okay. Then you check. P13. P13 multiply XYZ. Then what you get is X first column, Y the second column, Z the third column. Okay, so you get 0, 0, X, 0, Y, 0, and Z 0, 0. So you add them together, you get ZYX. I.e., the matrix P13 do this thing. Plug in XYZ, we output ZYX. Now this is the swap two rules. Okay. And we can also do rule multiplication. How do we do rule multiplication? Rule multiplication by scalar. So multiply rule operation. Multiply a rule. We want an operation that multiply a rule by lambda. Here lambda is not 0. Okay, we do the following. For instance, this matrix E lambda defined as lambda 1, 1. The diagonal, all diagonal terms are all 0. Okay, you check. Okay, then you see E lambda times XYZ. Then what we get is X the first column, lambda 0, 0, Y the second column, 0, 1, 0, Z the third column, 0, 0, 1. So you multiply by scalar. So this actually get a lambda X 0, 0. And you see this, you get a 0, Y, 0 plus Z. Sorry, it's a 0, 0, Z. Add them together, you see what we did using this operation E lambda is lambda X, Y, Z. You see the second rule and the third rule, they are fixed. And then the first rule, what we did to the first rule is we multiply the first rule by lambda. Okay, by lambda. Okay, by lambda. Okay. Now, of course, let's see. For instance, let's use another notation. Let's use M lambda. Let's use EFG maybe. F lambda to be 0, 1, 1. I.e., plug in I, output I, nothing, do nothing to I. Then plug in G, output lambda G. So we just multiply the second rule. So plug in K, output K. So this is multiply. So we get F lambda times XYZ. You can easily check using what we just did. So you get a X lambda Y Z. So this left lambda is multiplying the second column. Sorry, multiplying the second rule by lambda. Okay, you see, we can achieve this we can achieve this by rule operation. We can achieve this rule operation multiplying a scalar lambda by matrix. Okay, by matrix. Of course, you can replace G lambda, for instance. Let this to be this y1 lambda. Then all other entries are 0. So what this matrix G does is G lambda times XYZ. Its output is XY lambda Z. Lambda Z. Okay, that's very easy. Very easy. So we can do rule operation multiplying a rule by non-zero scalar. Now we have another rule operation. Okay, add a non-zero multiple of a rule to another rule. Okay, so this example, what we do is this. Let's see this. Let's this E to be this matrix definition. 0, y, y. So the first column is y -2, 0. Second column is 0, y, 0. I.e. plug in G, output G. Now third column, plug in K, output K. Look at this. Now we see what it did. This E does. E does to X, Y, Z. E does a vector X, Y, Z. Now you see the X goes to the first component, goes to X, the first column. Remember, the first column tells us the input of I, the output of I. The second column tells us the output of J. The third column tells us the output of K. Okay, now you see here, X, we get yx -2x, 0. Now the second, we get 0y, 0. The third, we get z, 0, 0, z. You put them together, then what you get is x, Q fixed. Then the second column, second rule becomes y -2x. Third rule is z. I.e., you see what this vector does, this matrix does to a vector is, you see, this is x, y, z goes to either the matrix E. We get an x, the first column, the first rule is fixed. The second rule becomes y, but subject to x. Okay, so this matrix does is we subject, we add -2 multiple of rule 1 to rule 2. Okay, z is fixed. So what this E does is, negative rule 1 plus rule 2, replace rule 2. All other rule is fixed. Okay, so this does the thing to a vector, If you have another vector, this does the thing again to that vector. Okay, so then this actually, this does the thing to a rule, Okay. So this is what this matrix E does. Of course, you can multiply. So you see the key thing is this factor 2. Let me highlight that. You see highlight. So you see this 2, this -2 under the entry 1. Okay. So this actually means we add -2 multiple of rule 1 to rule 2. Okay, rule 2. So this is negative. You see the -2. The -2 is, so this -2 is in the first rule, second, sorry, it's the second rule, first column. Second rule. Okay, second rule. So this means we add first column. This means we add to the second rule of the first rule. Okay. Now, if you multiply that thing, for instance, E to be 1, 0, -3. Okay, 0, 1, 0, 0, 0, 1. So then what if E defined to be the thing? Then what E does? What this matrix E does? What does this E? So what is E times XYZ? What do we get? What does this matrix E do to a vector? Anyone know?
It'll be X, Y, and then in the bottom row, it'll be Z minus 3X.
That's perfect. Yes. What is E? The matrix E does. The E subtract the third rule by by 3 times the first rule. Okay. So this E does is so we negative 3 rule 1 plus rule 3. Substitute the rule 3. Okay. Substitute the rule 3. Okay, let's see another matrix. For instance, let's see this E to be defined as this. Y 0 0. Now let's see this is 1. Let's see negative 2 here. Y 0 0. Okay, what does this E do? E X Y Z. Question: what does this E do? You plug in X Y Z.
Is it gonna be X minus 2Y and then Y and then Z?
Good. Yes, that's correct. So this E does is we multiply negative 2 to root 2. This negative 2 root 2 plus root 1. Substitute the root 1. Okay, substitute root 1. Okay, good. Now, if we do vectors, then we can also, if a matrix X on a vector, we can also define matrix operation. We already defined matrix operation as a composition of maps between vector space. We can also to define matrix operation in certain manner. Okay, matrix multiplication. Matrix multiplication. Now, for instance, matrix multiplication. Now, suppose A, B, they are matrix. A, B, A multiply B. Now here, A, B are matrix. Now B, if we write the column vectors, B1, B2, B3, B3. Now we can distribute. So you can view this as definition, or use check the definition we defined for matrix multiplication. So we use matrix. Okay, so here B1, B2, B3 are B1, B2, B3 are column vectors. Okay, now of course we should make sure that A and B, they should have certain size such that this makes sense, this map makes sense. So if A is Mn, M by N, M, so it's M rule, N columns. Now B, the only requirement such that the composition makes sense is, so here you see the two numbers, M times another number, maybe S, or maybe R. R is used for rule. Let's use T. Let's see. Okay, so you see, this is N rules, T columns for B. Okay, such that we need to make sure the column number of A should agree with the root number of B, such that they can compose in this manner. Okay, such that they can compose in this manner. Okay. Okay. For instance, let's see this matrix E and A. Let's E define as what we just defined. Example. E as y negative 2, 0, 0, 1, 0, 0, 0, 1. So what this E does is negative 2 root 1 plus root 2 replace root 2. Now this A to be this matrix 2, 4, negative 2, 4, 9, negative 3, negative 2, negative 3, 7. Well, for this matrix A, if we want to, elimination, okay? Suppose this A is coefficient matrix for a certain linear system. If we do linear, if we do elimination, so you see, we should, the second rule, the first entry of the second rule is 4. So we want to cancel that 4. So we can use twice 2 times root 1 plus root 2, replace to root 2. Okay. So you see, what we do is we use E, use the operation of E times A, E times A. Now, this is actually E, X on the 3 column vectors. Okay. EX on the 3 column vectors. Now, for each column vector, we add negative 2 multiple of the first component, but then add to the second component. Okay, so this will be fixed. 2, the first column is, the first entry is 2. The second thing will be 4 minus 2 times 2. Okay, the negative 2 is fixed. Now the second column 4 is fixed. And then 9 minus 2 times 4, 2 times the first, twice times the first entry. Okay, and then negative 3. And then negative 2, negative 3 minus 2 times negative 2. This will be 7 keep it fixed. So that you see what we get is, this will be 2, 0, negative 2. Okay, so this will be 4, this will be 1, negative 3. And this will be negative 2, this will be 1, this will be 7. Okay, now we can use another operation. Use another operation to, this is root 1, root 2, root 3.
Isn't this the same as the regular elimination though?
Yes. What we just did is elimination, but we use matrix multiplication. We will use elimination. We achieve this elimination, rule operation by matrix multiplication. Okay, by operation. Okay, we achieve this operation by matrix. Okay, this is the idea. Okay, once we know how to do certain rule operations, okay, use certain operations such that we can recover a matrix in inverse. So suppose we have a matrix A, suppose we use elementary matrix operations such that we make it to be I, okay, then A translated to I, then I, so what we did is actually, essentially we just did the inverse, okay. Now I, if we do this thing, under this thing, if we start with I, if we do A inverse, then we should get A inverse, okay. So the inverse operation is actually certain operations by matrix, okay. So we did elimination by rule operations. Okay, and the rule operations can be achieved by elementary matrix. I.e., we do certain operations by elementary matrix. Such that use this elementary matrix, we can transform a matrix, invertible matrix to I, identity, and then under the same operation, we will translate this I into A inverse, okay? Such that, so this is the idea. Now this is the idea of Gauss-Jordan elimination. Now we actually determine if a matrix A is invertible, and if it is invertible, how do we find its inverse? Okay, so this is Gauss-Jordan algorithm. Okay, Gauss-Jordan algorithm says the following. Okay, Gauss-Jordan says this. Suppose we have invertible matrix, you know, or invertible matrix should be a square matrix. This matrix A is invertible. We put an identity matrix of the same size. Okay, and then we do elementary rule operations. And then A subset rule operations, maybe multiple operations. Such that A transformed to I, identity, and then identity we transform to A inverse. Okay. Do the same operation, to do the same rule operations to A and to I. Okay. Okay, let's see some example. Okay, so suppose we just do a trivial example. A is 0, 1, 1, 0. Remember what does this A does? This A, you know, swap this matrix A, swaps the two rules, rule 1 with rule 2. Okay, rule 1 with rule 2. Rule 1, switch rule 1 with rule 2. Remember this swap, if we do it again, so we should get itself. So A squared is I. Remember, A squared is I. So actually the inverse is just A itself. A inverse is just itself. A inverse is just A itself. So you see, if we do this, we put the matrix A and I, matrix I. Now A is 2 by 2. You see, this will be A is 0, 1, 1, 0. Now I is 1, 1, 0, 0. Now, how do we transform A into I? Remember, to transform A into I, we swap the two rules, okay? What we did is R1 switch with R2. R1 switch with R2. You see? R1 switch with I2, R2. Then you see what we get is the first rule becomes second rule. Now similarly for the right side, the matrix I, the first rule becomes the second rule. Okay, the second rule becomes the first rule. The second rule becomes the first rule. You see this is I, this corresponds to I. So you see what A inverse? What do you get for A inverse? You see A inverse is this, which is just exactly A, okay? Which is exactly A. Okay, more example. This matrix A is 1, 2, 0, 1. Okay, remember what this A does. This A is actually elementary matrix, what we just did. Anyone know what this A does? What does this A does?
So you would have x and then x plus 2y. Or I'm sorry, 2x plus y.
Yes, good. So this matrix A actually tells us that A is we add twice root 1 to root 2. Okay. Now how do we, if we do this operation A, how do we recover original thing again? So we add 2 multiple of root 1. How do we recover the root 2 to our original root 2? If we added it, we already added 2 multiple of root 1. What should we do? What's the addition? What's the inverse of addition? We added 2 multiple of root 1. And then to recover, we should subtract twice of root 1. Okay? Such that nothing changes to root 2. Okay? And then root 1 is nothing changed. Okay, so what we should expect? What should be A inverse? What does A inverse do? A inverse should be
Just
go ahead.
just swap the columns.
You know, what A does is add 2 multiple of root 1 to root 2. Okay? Addition, add 2 multiple of root 1 to root 2. Now, to recover root 2, we should subtract. If we do A, and then we should, if we apply A, we already add 2 multiple of root 1 to root 2. Now, to recover root 2, to original thing, we should subtract, okay? Subtract 2 multiple of root 1. So that root 2 does not change, okay? So A1 should do, what A inverse should do is we add -2 multiple of root 1 to root 2, okay? Addition is, you see, addition and subtraction, they are inverse, okay? They are inverse. So they cancel each other, okay? So this should be -2x plus y. Okay, so that they cancel each other. Addition, subtraction cancel each other. So you see, if we do A inverse AXY, you see this AXY. This is x 2x plus y. Add root 2 by 2 copy of root 1, 2 multiple of root 1. Okay. And then A inverse does is this root 2 subtract 2 multiple of root 1, which is 2x. You see, addition and subtract cancel each other, okay? So that you get x and y, which is exactly the original thing. So this means A inverse and A is, of course, no surprise, identity, nothing changes. Plug in xy, output xy. Nothing changes, no change at all, okay? So now we can check this by Gauss-Jordan algorithm. You see, we 1, 1, 2. This is A, and this is I, 1, 1, 0, 0. So this is AI. Okay, then transform the thing. Transformer, such that we want some rule operation such that we get A transform to I identity, and then I transform into A inverse. Okay. Now how do we? You see the I is, remember I is 1, 1, 0, 0. So what we did, the rule operation is if we compare A with I, you see we have some extra 2 at the, you see, if we compare with I, compare A with I, okay? So that we should make this 2 at the left lower corner to be 0. What we do is we do rule operations. We add -2 root 1 to root 2, and then substitute root 2. such that you see this 0, this will be 2 will cancel to be 0. Okay, and then here we also do the same thing to the identity matrix, you see. So this 1 we should multiply -2 and then add to 0. Then what we get is this we get -2. Okay, this we get a -2. Okay, now the first column, the first row is fixed. So this is 1, this is 0. And then this 1 subtract 2 copy of 1, 0. So this is again 1. Okay, so you see this correspond to I, this correspondence. This correspondence is the I, this is the I, and by this correspondence, and this is the A inverse, and then this is the A inverse. So you see exactly A inverse is. So you see exactly A inverse is as we expected. This is indeed A inverse according to the rules that we did. Okay. So this is Gauss-Jordan. Okay. Now let's see one less trivial example. Now this A is 1, 5, 2, 11. Now this matrix A is complicated because it's not obvious. This A is no longer elementary operations. Okay, it's not elementary operations. So this operation is complicated. So, however, we can decompose. This thing, a matrix, by elementary operations. Okay, this corresponds to rule operations. We can do elimination such that we recover identity matrix. Okay, so use Gauss-Jordan. This will be write A and I identity matrix here. This is of course 2 by 2. So we write 1, 2, 5, 11, and this is a 1, 1, 0, 0. Okay. Now we do rule operations such that we transform the left side matrix A into identity, and then the right side identity matrix will transform to A inverse. Okay. So we do rule operations. So first of all, we cancel the 5 on the second rule. So we use this 1, negative multiple, -5 multiple of 1, rule 1, add to rule 2. Then replace rule 2 by that thing. So do this thing and see what we get. So rule 1 is fixed. Now rule 2, 5 plus -5, -1 times plus -5 times 1, so this is 0. Now 11 plus 2 times -5, 11 subtract 10. 11 subtract 10, we get 1. So this we get 0 minus 5, 1. So this is -5, and this 1 minus 5 times 0. This is the 1 minus 0, which is 1. All right. Then you see we needed, so the identity, remember, identity should be 1, 1, 0, 0. So if you compare, we have extra 2. So we need to deal with the extra 2. Now we need to cancel, we still need to, so this is extra 2. So to cancel the extra 2, we do rule operation again. So we let negative root 2. Sorry, let's do negative root 2. Let negative root 2 plus root 1, replace root 1. Replace root 1. You see root 2. The entry below the factor 2 is 1. So we we multiply -2, so we get a -2. Then -2, we can use -2, cancel 2 by addition. So this will get 1, this 2 plus -2, so we get a 0. Now the second column fixed. Now here, this entry 1, but we need a plus -2 multiple of the second rule, which is 5, -5 times -2, which is 10. So this is 11. And this is actually -2 multiple of √2, so it's -2 plus 0. Okay, so that if you compare, so this is I, this is equal to I, this matrix is A inverse. So we can get A inverse. A inverse is 11, -5, -2, 1. Okay. So if you check, remember A, what is A? A is 1, 5, 2, 11. Okay, if you multiply A times A inverse. Okay, you see what is the A times the vector 11, -5? So this is a 1, 5, 2, 11 times 11, -5. So you can use rule operation, use rule picture or column picture. If you use rule picture, if you use column picture, so this will be 11 multiple of 1, 5 minus 5 multiple of 2, 11. So this will be 11, 55. Subtract, this is 10, 55. So this is the 1, 0. Okay. Or you use a rule picture, you use dot product. Okay. Now A times the second column, -1. So this will be the first column, -2 times 1, 5 plus the second column, 2, 11. So this will be -2, 10, -10 plus 2, 11. So this you get exactly 0, 1. So you see the multiplication is the first column is 0, 1, 1, 0. The second column is 0, 1, which is exactly identity. The diagonal are all 1. The off diagonal terms are all 0. So this gives us identity. Okay. Okay, this is actually important. We have the first algorithm how to compute the inverse of a matrix. I.e., we're using elimination. We use Gauss-Jordan elimination. Use elementary rule operations so that we can recover, so that we can find the inverse of a matrix. Okay, this is important. Homework problem for these sections. Okay, homework for 2.3 is try to use this algorithm, Gauss-Jordan, to do some practice. Okay. All right, now let's continue with the next topic. Matrix operations, rule for matrix multiplications. This section is actually easier. Okay. see, section 2.4, rules for matrix multiplication. Okay. Okay, for matrix multiplication, we can either use row picture or column picture. They are actually equivalent. So we already know how to do that already. So suppose x is a vector, a times a vector, a matrix multiply x on a vector. So suppose A is column vector C1, C2, C3. Okay, and then the rule, the x is xyz. Remember, the first column gives us the output of I. The first component. The second column gives us the output for the j. The third column gives us the output for k. Okay, so this corresponds to. You can view this as definition. So this is x c1 plus y c2 plus z c3. Okay. So you see, we have the x vector. We have 3 components x, y, z, and each component corresponds to the columns. Okay. So that to make sure that a vector, a matrix multiply a vector makes sense, we should make sure the number of columns of the matrix A should equal to the number of the components of X. Okay, so the number to make sure this makes sense, the number of columns of A equal to number of rows or components, number of rows of vector X. Okay, now if we have matrix B, we can write as, B is a matrix. If we write B as column vector x1, x2, x3, 3 columns, then here xi is xi, yi, zi, okay, I equal to 1 to 3. Then we mount a matrix multiplication. You can use the same technique we obtained by, as matrix, view matrix as maps between vector spaces to derive how they compose, okay, to derive the product formula. But here we will not do that again. You can view this as definition, because if you unravel that machinery, then what you essentially get is actually this thing. So this definition is not a bizarre operation. So this is actually the most natural thing. It's a unique thing that we should define matrix multiplication in this manner. Okay. Okay. So here the number of, here, because we should define A times X. So we need to make sure the rule of X is the same thing as the rule of B, okay? So to make sure this makes sense, so this number of columns of A equal to number of rows of vector xi for each xi. They are the same actually. x1, x2, x3. The vectors, they should have the same number of rows. Now, of course, this is equal to the number of rows of B, matrix B. i.e., if we have 2 matrix multiplication, A multiply a matrix B. Now, to make sure this makes sense, A times B. So we should make sure that A is n row, m row, n column. Now, so A should be m row, n column. So the second number is column number. Now B should be n row, and then T column. Okay, such that this number should coincide. Okay. Okay. Now, in the rule picture, we do the following. Okay. A is rule 1, rule 2, dot, dot, dot. Let's see, it's rule M rule. Now B is B1. So this is B. So rule picture. So this is A. B1, B2, BT. Now B is T column. Now A dot B, A times B. Actually, we get a matrix. So AB is A. Now shrink the number n with n. So this actually is M times T. Okay, M times T. So you can see n cancel n. So your remaining is M times T. So the IGS entry, I's column, I's row, G column, IGS entry of AB. So suppose let's see be AB. Then of the matrix C, the product AB is Cij is this matrix, this number. Dot product I's row dot product with G column. Okay. Now to make sure the dot product makes sense, we should make sure that the two vectors lies in the same vector space, i.e. So this is actually why we need require the column number of A should agree with the row number of B. Okay, such that we make sure that these two vectors lies in the same space of the same dimensional. So here I is from 1 to M, and J is from 1 to T. Okay. Here the vector is I's row of the vector of the matrix A. I's row. Now the column number of A is n. Okay, I is from 1 to M. BG is the column vector. B1G, this is the one. B1G, B2G, etc. BNG. You see, they have exactly the same number of components. So the dot product is the Euro dot product that we define. Okay, let's see one example. Compute use row picture and column picture. 1, 1, 2, -1, 2, 3, 2, 4. Okay, compute use the row picture. Now this entry, what do we get? This entry, the first row, first column. So we should use the first row, this AB. First row of AB, R1 is 1, 1. Okay. Now the first column of a B, B1 is 2, 3. So you see R1 dot B1.
So should it be 5?
Yes. So it's the 1 times 2 plus 1 times 3. So it's 2 plus 3, 5. So it's the 5. Okay. Now this 1, 2. So it's a B2. B2 is 2, 4. Okay, so the first row, second column, so this will be R1 dot B2. So this is actually, 1, this will be 1, 1 dot product, so 1, 1 dot product with 2, 4. So this will be 2 plus 4, which is 6. So the first row, second column will be 6. Okay, will be 6. So this, we get this 6. So this we get a 5. But then, so this will be second row, first column. So second row, first column. So it's R2 is, you see, R2. The second row of second row, which is 2, negative 1. Now B1 is, we already know, B1 is 2, 3. So second row, first column, R2 dot B1 is 2, negative 1 times 2, 3. So you get a component-wise multiplication and then add. So this is actually 1. So we get this 1 should be here, so 1. Okay, then R2 B2 gives us the 2, 2 entry. So R2 is, we already have R2, is 2, negative 1. B2 is, what is B2? B2 is 2, 4. So this will be 2 times 2 minus 1 times 4, which is 0. So this 0 corresponds to the 2, 2 entry. 2, 2 entry. Second row, second column. So which should be here. This thing is 0. So you see we get A times B is this thing. Okay, so we get this multiplication is 5, 6, 1, 0. Okay, now if we use column picture, what do we get? Column picture, the first rule is 1, 2, the matrix A times the first column, 2, 3. Now column picture. Now we should get 2 times the first column and then 3 times the second column, which is 2, 4 plus 3, negative 3. You see, add them together component wise. So this is 5, negative 1. 5, 1. You see, 5, 1 is exactly, if you write the thing, you see this is exactly the same. 5, 1, and then you have 5, 1. They correspond to each other. Yeah. Now, if you do the second column, you do the second column, 1, 2, 1, negative 1. Second column, it's a 2, 4. Okay. Then what we get is 2 multiple of first rule and 4 multiple of second rule. And then this you get 2, 4. And this you get a 4, negative 4. So you add them together, you get 6, 0. And you see 6, 0 with 6, 0. This is the highlighter. You see this 6, 0. And here, here we have 6, 0. They are actually correspond to each other. Okay, so to multiply a matrix multiplication, you can either use rule picture or you can use a column picture. They are equivalent. Maybe sometimes it's easier use rule operation. Sometimes it may be easier use column picture. We will actually require both methods to know rule picture and column picture. We will use this again and again in this course, rule picture and column picture. Okay, now matrix operation, we can add to matrix, we can multiply to matrix. So here there are some trivial property. So addition of matrix, that's easy. That makes a vector, that makes matrix into a vector space. Okay, you have a vector space of matrix. So they are commutative. So matrix addition, they are commutative. So properties of some matrix operations. Commutative, and then distribute scalar. You can distribute a scalar. And of course, you can distribute a matrix multiplication. So you can left multiplication, you have a right distribute multiplication. So you can also have this. This trivial. This is not trivial. CA plus CB. And also association of addition. That's trivial. And then association with multiplication. Now, in general, matrix multiplication is not commutative. Matrix multiplication is not commutative. In general, this fails. Okay, this fails. Okay, this fails. Now, if you study physics, there's a theory, there's a subject called quantum mechanics. Okay, now the old name for quantum mechanics is called matrix mechanics. Okay, matrix mechanics. Now, in this quantum mechanics or matrix mechanics, now physics is based on experiment. Experiment is based on measurement. Okay, you should talk. You cannot design certain beautiful model for physics that does not coincide with experiment. That's not physics. Physics is based on experiment. Experiment is based on a measurement. Now, the measurement of a quantity, physics quantity, in quantum physics correspond to a matrix. Okay, correspond to a matrix. Now, you see matrix, if you do twice measurement, measure one quantity and measure another quantity. Now, this corresponds to a matrix A and a matrix B. Now, if you measure A with measure B first or measure A first, they correspond different kind of a thing, matrix. And then it turns out, if you measure one quantity and measure another quantity, or switch the order of which measure first, now it turns out they can different. This kind different. So this actually is a lot different from classical mechanics. Okay, classical mechanics, believe that if you measure this quantity and this quantity, different quantity, now that should be a unique defined quantity for the things. They do not involved with each other. However, quantum theory says this is not the case. This is not the case. Now, linear algebra is really important, especially if you study quantum mechanics. Because quantum mechanics is, its name, matrix mechanics. You should use matrix everywhere. Okay. That's pretty trivial. A, B equal to not B, A. For instance, let's see one example. A is 1200, B is 1300. Let's see what A times B is. 1200 times B 1300. Okay, let's just use the first row times the first column. 1 times y, 2 times 3. Okay, add them together, so we get 7. The first row times the second column. First row 1, 2. Second column 0, 0. So this got 0. Now the second row times the first column. Second row times, because the second row of A is just 0, 0. You multiply anything, we get a 0, 0. Okay. Okay. Now if we BA is 1, 3, 0, 0 times 1, 2. Now the first root times the first column. The first root 1, 0 times 1, 0, the first column. Now dot product gives us is 1. Now the first root times the second column, the thing, okay? Now the second root times the first column, we get a 3 plus 0. Now the second root times the first column, second column, we get a 6, okay? So you see AB is different than BA, okay? So it's in general, it's not a commutative matrix. Now if you do math, commutative object is called abelian. Abelian group means abelian means commutative. Abelian group, if you study group theory, abelian means commutative. Now non-commutative means non-abelian. Okay, you see non-abelian group, i.e. you can not switch AB with BA. Okay, now let's do some more examples. Now, of course, we define matrix multiplication, then it makes sense. This for instance, A is 1, B, 1, 0, 1. Now this A is actually elementary matrix. Elementary matrix. Remember what this A does? What does this A do? A x y is, you see, this 1, 0, B, 1, x y. What this matrix A does is we add B multiple of, so this A does, what this A does is we add B multiple of root 2 to root 1. B multiple of root 2 plus root 1 replace root 1, i.e. we add B multiple of root 2 to root 1. Okay, so this, if you unravel the definition or you just compute it, so this is actually B plus x plus by. Okay. Okay, the first component is the first root 1b dot product with xy. Then you get x plus by. The second root is the second root dot product with xy. The second root is 0, 1. 0, 1, you see 0, 1 dot product with xy, which is actually 0 times x plus 1 times y, which is just y. Gives us the second component of y. The first component 1b dot product with xy gives us 1 times x plus b times y. So it's x plus by, which gives us the first component. Okay. Okay, now without computation, what does A2 does? A squared. A squared means we do the operation of A, and then we do the operation of A again. Now this actually, without computation, just use common sense, what do we get? What does A squared does? A squared means A. Okay. Now A add B multiple of root 2 to root 1. Now if we do this thing A again, then we add B multiple of root 2 again to root 1. So then we, in total, we write 2B copy of 2B multiple of root 2 to root 1. So this actually, what this A squared does is 2B root 2 added to root 1, okay? i.e. 2B root 2 plus root 1 replace root 1. i.e. we add 2B copy of root 2 to root 1, okay? So if you write the thing as elementary matrix, then you see what we get is use elementary matrix. So we should get the thing. Okay. Now similarly, what do we get at A3? What do we get for A3? Anyone know? What do we get for A3? How do we write down A3 without a computation?
3b.
3b, good. Now, A5, of course, we get it without computation. Now, this is very tedious if you compute this A5. You got a 5b here, 1, 1, 0. In general, an for integer n. Now, remember here, the exponent, this means we only define integer, okay, integer. NB. Now the square root, if it's a square root, it doesn't make sense right now, okay? Doesn't make sense. But A inverse makes sense. This A inverse makes sense. It's negative b, okay? This can easily checked. A inverse. Okay. Okay, more examples. This example. A equal to this. Now, of course, A is non-zero matrix. Okay, sometimes we abuse notation. If it's a zero matrix, it's really redundant to write every zero all the time. So we just abuse our notation. If it's zero everywhere, we just write 1 0. And claim it's just zero matrix. Okay, by abuse our notation. Now for this A to be this 1 0 1 0 0. So A squared is A times A. You check, what do we get? The first root times the first column. The first root times the first column. The first root is 0 1. The first column is 0 0. You dot product, you get a 0. The first row with the second column 0 1 1 0. The dot product, you get a 0. Now the second row 0 0 dot product anything, you get a 0. So this actually abuse of notation is 0. So here this 0 is not a scalar 0. So it's a matrix 0. Abuse of notation. You know, if you write all the zeros, it's just really ugly. So we just prefer to at a little risk of abuse of notation, but it's more elegant to write in this manner. So you see here, A is non-zero. A is non-zero. But you see A squared is 0. So this is the key difference with real numbers, okay? Real number, a non-zero number, you raise it to any power, you never get a 0. So this is actually a different phenomenon with lower dimensional case, the real number case. So here, a matrix A, if some power of this matrix A becomes a 0 matrix, then this thing plays a special key property. Definition. A square matrix A is called a nilpotent matrix. Nilpotent. If A raised some power n is 0 for some n in, let's see Z, let's see natural number, okay, for some n natural number. So we already have one example of nilpotent matrix, okay, nilpotent matrix A, you know, so example. A equal to 0 1 0 0 is nilpotent. nilpotent. Okay. Now, nilpotent matrix actually plays a really important role. It's actually interesting. It has nice property. Fact. What matrix can be nilpotent? Any upper triangular matrix with 0 on the diagonals. Any triangular matrix with zeros along the diagonal. The main diagonal. The main diagonal is the diagonal. Is nilpotent. But this is only part of the nilpotent matrix. It's possible that we have a non-zero matrix that none of the entry is 0, but you raise some power, you get actually 0. Okay. So this is only a part of a nilpotent. This is not all nilpotent matrix of this form. Okay. Okay. Now let's give one example maybe about the property of the nilpotent matrix theorem. This theorem. If A is important, then identity matrix such that A is invertible. Is invertible. Okay. Proof. Now A is nilpotent by definition. This implies A to some power n is 0. Okay. For some n. For some n in natural number. Then you see we have this. Then we apply the geometric series. Looks like the geometric times I plus A plus A. Okay, here is A and I. A and I, they are commutative. Okay, because we don't have any other. A is commutative with A. Okay, so this is actually, we essentially use A times A minus X plus use this identity geometric series. So this is actually 1 minus X to the power n. Okay, we use this algebra. Okay, we use the algebra. Okay, so you can so this apply to the matrix because here we essentially use algebra cancellation. So you can check. This is again after cancellation. This you get a this thing. Okay. Now because we know A to the power n is 0 matrix, so this is I minus 0 matrix, which is I. So you see we have I minus A is left inverse. Now if you switch, you can also, this is left inverse, also right inverse. So this is actually we have an inverse. Okay, inverse. So of course this, if you multiply on the left, again you get the same thing. So a left inverse is also a right inverse, although this is not obvious. Okay, for in general to prove that. So this is also I minus A n. This is again I minus 0. This is again I. So this is actually left. This is also left inverse and also right inverse. So it's inverse. So actually we know I minus A is invertible. Actually we also find it what this inverse is. What its inverse is. Okay. Now homework for this section. Homework. 3, 12, 15. number 21 to 24, number 32, number 33. Okay. Okay, it's maybe let me stop here and continue tomorrow.